the second episode of our series, Simvia Insider. Today we will have the pleasure to know a little bit more about computational fluid dynamics with the open source solver CodeStation. And with us we will have Florian Hermé and Mariam Kesba. They are both CFD engineers at Simvia. And we will see how at Simvia we use CodeStation and how we automate all the simulations that we need to do with an open source project that we have at Simvia. Right now, it's my pleasure to introduce you, Mariam. I think you will start.
Hello, everyone. So before we dive into CSO2, let me give you a quick introduction about CodeStation. So CodeStation is a finite volume CFD software that is developed by EDF R&D since 1997. So it solves the Navier-Stokes equations for 2D, 3D flows, laminar, turbulent, steady, and unsteady flows. It can also handle incompressible, deletable, or weakly compressible flows. And what is really remarkable about CodeStation is that it comes with a broad range of specific physics modules, such as the Lagrangian particle tracking, atmospheric flows, electric arcs, and many others. So now if we take a look in terms of numerics, so CodeStation takes unstructured or hybrid meshes, which means that it can solve any cell types, and it can also do branch LES and hybrid DDS flows. If you take a look at the scalability, we can say that CodeStation is a massively parallel code. It has been proven on several HPC clusters, and many simulations were done with meshes that have hundreds of millions of cells. What is also really interesting is the ecosystem around CodeStation, which makes it very easy to use because it has a built-in GUI, and it can be made really you can personalize your cases as much as you want with C++ user functions. It is also important to note that it can handle several mesh types, and it can also output in whichever mesh type you want, and you can afterwards visualize your outputs with PowerView, for example. So all of this to say that CodeStation really is an industrial-grade open source CFD software. So now let's talk about installing CodeStation. So there are several ways to do so. So the historic way is to build from the source, and in this case you would have to install and compile every dependency. So what we will present to you today is to install CodeStation via Docker. So it's just important to note that for CSO2 you can use whichever installation you want. But if you do not have yet a CodeStation installation, we recommend you to do it via our Docker Hub, because it's just very quick to install. So now I will show you a live demo of how you can retrieve our CodeStation installation from the Simvia Docker Hub. So on your terminal, you can do a Docker pull Simvia CodeStation latest. So this will automatically fetch the latest CodeStation version available on our website. Afterwards, you will add this alias to your bash RC, for example, so you don't have to type it each time in this terminal. And then to make sure that your installation worked well, you will run CodeStation help. And if you have this output, then this means that you're all set and that CodeStation was well installed. So now I will show you quickly how you can set up a test case. So the case I will be presenting to you today is a flat plate is a 2D flat plate where you will try to see the development of the turbulent boundary layer. So to create the test case, you need to run this command. So code Saturn, it uses the alias that we have defined earlier. You see that you have the case folder. And to open it with our Docker installation, you type code Saturn GUI and the path to the setup XML. So this will it will display the GUI. And to show you quickly how to set up the case, so here we do the mesh directly via the code Saturn interface. Because since it's a flat plate, code Saturn can generate Cartesian mesh. So it was easier to do it this way for this case. But of course, you can import your mesh in the extension you want. Here we define the boundary conditions. And here for the calculation features, you define what models you want. So here it's an incompressible flow. We do not define any body forces. For the turbulence model, we use the Omega SST. And in terms of boundary conditions, here we have the inlet, the outlet, the wall, and the symmetry, since it's a 2D case. So here you have the different options for the boundary conditions. Now, if you take a look at the time settings, this is a steady flow. We can also see the different parameters that you have to set up for the steady flows for this case. Here we do not do a restart. So this part is just to show you that automatically code Saturn offers default parameters, but you can of course change them with whichever you want. For the schemes also and the gradient. Also, if you want to do clipping on specific variables, you can do so. And here comes the post-processing, what you want to process. You can also add monitoring points if you're interested in a specific part of your domain. You can also add a profile like we did here for the velocity, for example. And you define the coordinates of your line. So here, I will run the test and choose a number of processors. And then I will run the simulation. So in the GUI, you can go to the convergence tool to monitor your case. So this is a live display of the simulation. So here you have the residuals. And then on the second plot, you can also, for example, see on the probes that we defined in the post-processing before, you can also visualize the values like this. It appears on the second graph. So this is just to show you how we set up one case of in code Saturn. So this will create a .setup.xml. It will update it with the parameters you did it. So now I'll pass the hand to Florian to explain to you how we can do parametric studies more efficiently.
Thank you, Mariam, for your presentation. Now imagine that we want to perform a parametric study with code Saturn. For instance, we want to evaluate the influence of a boundary condition, a turbulence model, or a mesh refinement on our results. We need to perform several simulations to do that. For instance, if we want to perform 40 simulations, the problem with code Saturn is very clear. We need to open 40 GUI sessions. And consequently, it can take a lot of time, and there are a high risk of human error because you need to perform to change at the end manually all the value in the GUI session. So it is very time consuming, and there are a high risk of human error. Before CS Auto in the code Saturn ecosystem, there wasn't a tool which allowed to manage a parametric study, to perform a parametric study, and to monitor a parametric study simultaneously. Consequently, at Simvia, we decided to build a tool which allows to do that, and this tool is called CSAuto. So it allows to prepare in a very efficient way all the case of our parametric studies, thanks to batch case generation. It's allowed to monitor the convergence of our parametric study, thanks to a web dashboard. It allows to detect the error and the warning within our computations. It allows also to compare some run between them. And it can be used on your local personal computer or on HPC, thanks to Slurm environment. How CSAuto was designed at Simvia. So to design CSAuto, in fact, at the beginning, we had three key principles in our mind. We wanted a tool which allowed to prepare in a very efficient way all the parametric study. That is to say, to prepare all the input file of CodeSaturn. We wanted a tool which allowed to run our simulation and to track the status of the computation, which computation are running, which computation are pending, which computation are crashed. And we wanted also a tool which allowed to monitor our computation in order to follow the convergence, the error, or the performance of our simulation within our parametric study. So to do that, we wanted a tool which is very simple to use. For instance, the design of experiment of our parametric study is defined only in a CSV file. And why a CSV file? Because it is only a plain text and it can be opened in any text editor. We wanted also centralized monitoring thanks to a web dashboard in order to follow the status of our run and also the convergence of our run. And we wanted a tool with no external dependency, and consequently the tool is developed with a Python library. So now, if I will show you a quick tutorial of CodeSaturn, so I will launch the video and I will comment the video. So first, before to use CSAuto, we need to download and install CSAuto. So in fact, it can be done with only one command line, as you can see on the screen. And this command line can be found on our GitHub, on the GitHub of CSAuto, and the link of CSAuto GitHub is given at the end of the presentation. So with only one line, we download and install CSAuto. After to download and install CSAuto, we need to reload our bashrc in order to have access at all the CSAuto commands. And we can check the installation of CSAuto with CSAuto help command. So now I will copy an example folder of CSAuto in order to show you how CSAuto can be worked. So for that, I copy the example folder, which is located in the source of CSAuto. So you can see that in the folder of CSAuto, there are three subfolders, the mesh folder and the post folder, which are exactly similar than the mesh folder and post folder in a CodeSaturn study. And we can also see a template folder. So the template folder is very similar to the case folder in the study, but with some differences that I will comment. And we can also see two other files, CSAuto file and design of experiment CSV file. So the CSAuto file is the config file of CSAuto. So in the CSAuto config file, you need to define the installation path of your CodeSaturn install and the type of your installation. So here, for example, our installation is based on Docker, but it works also for Singularity installation or for a native installation. In the CSAuto config file, we need also to configure the host and the port that we want to open for the local web app. And we can also define a password if we want to connect at the local web app. Now, if I will comment the design of experiment file, so the DOE CSV file, so you can see that the format of the file is very simple. It's a column format, and in this format, in this file, in fact, we define all our design of experiment. So you can see that, for instance, here we want to perform 8 simulations in which the density value, the turbulence model, or the mesh will vary. And so we give the value, for instance, of the density or of the turbulence model. If I go in the template folder, so in the template folder, in fact, you have 2 subfolders, the data folder and the SRC folder. In the data folder, you have the main input file of CodeSaturn, which is the setup XML file. And in fact, this file is completed when you complete the GUI session. In this case, we place some placeholder with a curve brace in order to change the value, for instance, of our mesh or our turbulence model. So you can see that, for instance, here on the mesh name, we place some placeholder in order to replace this value by the value of the design of experiment. In the setup.xml file, we can also modify directly a large block of the XML file with if and if block, as you can see here. So, for instance, here we put directly if and if block. And if the spiral Morris turbulence model is selected, we apply directly all this block of command. Why we do that? Because if you want to perform a spiral Morris turbulence model simulation or a Omega SST turbulence model simulation, you don't have exactly the same number of equations to solve, and consequently, it is not exactly the same parameter. Also, we can see that in the template folder, we have the SRC subfolder. So the SRC subfolder is a folder in which we have the user function of CodeSaturn, which are very similar to the user-defined function of Fluent. And the user function of CodeSaturn are C++ file, and in this C++ file, we can also place some placeholder with curve brace, which will be replaced by the value of the design of experiment CSV file. When our template is ready, we can prepare our case. And so it can be done with a command of CSAuto, which is the CSAuto prepare command. So in this command, we give 2 input arguments, the design of experiment file and the template folder, and we give 1 output argument, which is the runs folder in which all the case will be generated. So we can see that after to type this command, we have now the run folder in our study. And if we open the run folder, we can see that we have now 8 cases. And if we open, for instance, the setup file of this case, we can see that, for instance, the density value here is replaced by the value of the design of experiment file. Now, after to prepare our parametric study, we want to run our parametric studies. And for that, we need to start the web app, and so it can be done with the serve command on the output directory of our study. So now, if we go on our local navigator and if we open the host and the port that we specify in the CSAuto config file, we can open the CSAuto web app. So here you can see the CSAuto web app. So here the local host corresponds to the host given here. The port is also corresponding. Now we can see that the web app is organized by tab. The first tab is the status tab, in which we can see all the computation that we plan to perform. So we can see our 8 computation with the design of experiment value, for instance, the value of density. We can also track the status of our computation. So here, for instance, our computation are only prepared but not run again. And if we want, we can run some computation. So for instance, if we select the case 1, and if we click on run, we can select the number of MPI process that we want, the number of CPU, and the number of thread OMP that we want to perform the computation. So we can run our simulation. So we can see that the status of the simulation is changing. We can see that our simulation is running. We can run another simulation if we want. Now we can see that below the status tab, we have another tab which is a residual plot, and which allow to monitor the residual convergence of our simulation. So for instance, if we click on the case 1, we can see our residual, the evolution of our residual according to the iteration of our simulation. We can compare several cases between them in order to follow the convergence and to check the convergence. So yes, here for instance the case 2 has not only 6 iterations, so we can compare the convergence across cases. Another tab which existing in the web app of CSAuto is the probe tab, which allow to monitor the probe convergence. For instance, if we put some probe in our flow in our simulation, we can follow the temporal evolution of some values on this probe. So here, for instance, we can see on the case 1 the evolution of our probe. Another tab is the timing snapshot tab, which allow to compute directly the computational efficiency of our computation. And this tab allow also to compare some case between them. So here we don't have any value because the case 1 and the case 2 has not finished again. But if we wait a little bit, for instance, for the case 1, we will see that we have now the computational performance of our simulation. Another tab within CSAuto is the side-by-side tab, which allow to compare two simulations between them. So it allow to compare directly several log files between them, and it is very useful if you want to debug some case, if you want to understand why in some computation the residuals are increasing or something like that. So it allows to directly compare two files. So we can see, for instance, in the run solver log file, we can directly see the difference between the case 1 and the case 2. Another tab in the web app is the log tail, which allow to follow the log during the computation. So it is it can be very useful. And the last tab is a tab which allow to diagnostic and to detect the error and the warning in our computation. For instance, if here for the case 1, you can see that we have several warning in the computation, and we can detect this warning. And so now, if our simulation is finished and converged, we can also mark our simulation as converged by a right click on the good line, and we can also run multiple cases at once. So yes, that is a quick demonstration of CSAuto, but don't hesitate to use CSAuto. Now, if I give you very quick tips to get the most out of CSAuto. So first, with CSAuto, we can add cases during our CFD campaign. Sometimes we run our CFD campaign, and during our CFD campaign, we want to add a new case or to delete some cases. And with CSAuto, we can do that very easily. So to do that, in fact, we need to go in the design of experiment file, and we need to add or to delete directly some line if we want to add a new case. After that, we need to run the prepare command in order to update our parametric state. So here, for instance, I added 2 new cases, and I rerun the prepare command to generate the new cases. And if I do that, and I will go on the local web app, I will see two new cases, the case 8 and the case 9, which doesn't exist before. And now, if I want to run, I can do that. Another tip is the fact that often we use Code Saturn on an HPC, and on the HPC we don't have a graphical display. Consequently, it can be complex to use CSAuto, but in fact we can also use CSAuto without a graphical display in the HPC servers, thanks to an SSH tunnel. So I will show you how to do that. So here I'm on the HPC server. So I put in place my study with CSAuto. I give the host and the port to open my web app. I prepare all my case with the prepare command. After that, I open the server on the HPC server, thanks to the serve command. And after that, I will go on my local machine, and on my local machine, I create an SSH tunnel with the good host and port, which are specified in the CSAuto config file. And now I'm able to run CSAuto on my local web navigator. So it can be very useful. Now, if I go on my local navigator with the good host and port to open the web app, I can run a computation with directly on my local computer on the HPC. So I can see that, for instance, the log tail is running, and if I go on the HPC, I will see that the run are the computation are running. So Yes, it was just 2 quick tips. What is the next for CS Auto? So in the coming week, we plan to add CS Auto at the Code Saturn container in order to facilitate the using of CS Auto. We plan to add some post-treatment capabilities at CS Auto. For instance, on the case that I run, if I want to directly investigate the aerodynamic coefficient of my simulation or the head losses of my simulation, we will add a capability for that. We plan also to have directly a design of experiment generator within CS Auto because usually, for instance, we run directly a factorial design of experiment, and it can be done very easily with CS Auto. And we also plan to have a system which allow to archive our campaign in order to restore and reproduce any run in the future. So don't hesitate. If you want to use CS Auto, you can download CS Auto directly on our GitHub, where the link is given here. You can open issues if you see some bugs or if you want some new features. Don't hesitate to contribute also with pull requests. So don't hesitate if you want to develop a new features or just to improve the documentation. Don't hesitate. So now we will finish our presentation. So don't hesitate if you have any question. We would love to hear from you. And don't hesitate to use CS Auto. The installation is very easy with only the 2 lines that you can see. So yeah.
Right. Thank you, Florian. Thank you, Mariam. I think we have time for one question. So the first one is: you plan to extend CS Auto at others CFD solvers?
For now, not. No, but maybe it can be a good thing to extend CS Auto at the other EDF solver, as for instance Codaster, if we want to plan to do some aeroelasticity simulation.
Okay, great. So yeah, once again, thank you.